Hi everyone, welcome. In this video, we are going to solve Mext exam problem for undergraduate program Physics 2015 number 2. So we have this question. Actually, this is not the whole question, but I just take the picture because it kind of conclude everything that we need and the picture of the question and some information which is not included in the picture. So first we have the conducting bar of mass M. This is the conducting bar, mass M. This is the side A, this is the side B. It slides without friction, so it will go down without friction. And the acceleration due to gravity is G. We have the magnetic field pointing upward, and then the length of the conducting bar is D. The plane is inclined at angle theta, and this system is connected to resistor R. So the first question is, which way does the current flow, from A to B or B to A? So here we need to recall the Lenz's law. So before we use the Lenz's law, let's review a bit about the Lenz's law. So here it is. The Lenz's law is this. I take it from Wikipedia. But the important thing is it will create induced magnetic field that oppose the changes of the initial magnetic field. Okay, you know what? I will tell you easier way to remember it. The system doesn't like being stagnant. It doesn't like changes. Okay, so if the B is increasing entering the system doesn't like changes, so the system will generate induced magnetic field to oppose the original magnetic field. It will generate induced magnetic field in opposing direction. If we decrease the magnetic field into the system doesn't like changes, so the system will try to increase back the magnetic field by adding more magnetic field with the same direction. So it is easier to remember that way. And in our question, this bar goes down. The area covered from when it goes down is getting larger. The total B included in that area is also increasing. So the system will try to decrease the magnetic field by generating induced magnetic field opposing direction. So from this picture, just now we have the magnetic field going up like this. So now the induced one will goes down like this. Let's say after time t, the conducting bars arrive at this point at time t. So this is the area covered. Okay. Now, using the right hand rule, we will get that the direction of the induced current is this way because it pointing down. The thumb is our magnetic field direction. It pointing down, and our four other finger is going like this. So you will, if you try, you will notice that the direction is this way, like the blue arrow. So it is from B to A. Okay, so the answer is from B to A. Okay, next, the bar is moving along the rails at the speed v, and the bar is always perpendicular to the rails. Which of the following is the correct formula for the induced current I? So before we calculate the induced current I, we need to calculate the electromotive force or EMF. Or maybe it is more familiar for you if you see V symbol. So EMF equals to minus the changes of the magnetic flux over time. And let's try to plug in the magnetic field, because magnetic field equals to the integral dot product of B dA, where dA is the changes in area, this. So let's put in to the equation, d over dt integral of B dot dA. Then let's redraw this so you can see it clearer. This is the inclined plane, and here is the theta. We have the bar over here, conducting bar, and we have the magnetic field going upward like this. So in our formula just now we have B dot dA. In which way dA, the direction of dA pointing to? So if the area, we have an area like this, so the direction of dA just the perpendicular of the area, so just like this. So in this case it is this way. Okay, this is dA, this direction of dA. And since this is theta, so this is also theta. This is 90 minus theta, so this is theta. So the angle between B and dA is theta. Now let's put it into the equation. We have d dt over B dA cosine. The angle is theta. Now B is constant. The value of B is constant. The theta is also constant. So we can take it out from the integral. We have d dt B cosine theta integral dA. Integral of dA is simply just saying calculate the area. So the area is this. What is the area of this rectangle? It is d times this side. D times this side is equal to the velocity times the time. We will get distance, then that is the side. Okay. Now we have B d v t cosine theta. Try to differentiate this equation. We have minus B d v cosine theta. Okay, this is the EMF. Now let's take that and put it here. Now we want the induced current I. We know that V is equals to I times R. The resistor, where here we have resistor equals R. So we arrange this. We have V over R. So we have, by the way, this sign is just indicating that the induced magnetic field that we have just now is opposing the changes. So just take the value of V. Take the value of V. We have B d v cosine theta over R. So the answer is F. Okay, now let's move on to the next question. Number 3. Besides gravity, the magnetic force acts on the bar. Find the correct formula for the component of this magnetic force along the inclined plane. Yeah, let's redraw the plane and the system again. Magnetic field, and this is our mass. mg. Okay, because of this B, we also have magnetic force X on the bar. If you recall, that magnetic force is equals to FB equals to IL cross B, magnetic B. So what is the L? L is just the length of the bar. The direction of vector L represents the direction of current I. It is just the same as saying ILB sinus the angle between the B and the L. So this is B and L is just going inside the paper. So the angle created is just simply 90 degrees. So we have ILB. But then what the question wants is not just the magnetic force, but the magnetic force along the inclined plane. So we need to break the, oh yeah, I haven't told you yet the direction of FB. So L cross B. L first. Just now we have that the direction of induced current is from B to A. So from this picture, it is just pointing outwards. So put your hands like without the thumb towards you, and then you try to move it to the B side. Then you got the thumb or going to the left. So that is the direction of FB. This is the direction of FB. Okay, but it wants the magnetic force along the inclined plane. So we need to break it into normal component and the component that is along the inclined plane. So this F is what we are looking for. Just now the theta is here, so the theta is also over here. As you can see, F equals to FB cosine theta. So ILB cosine theta. From the previous part, we already know that I equals to, let me check it again. Let me copy this part. And put it over here. We have I is actually B dV cosine theta over R. Then we have L B cosine theta. By the way, the L here is actually just the length of the bar. So L is actually D. Let's put it in to the equation. B dV cosine theta over R. This is the B cosine theta. I will write it here. Here D is equal, L is equals D. And then so now we get the answer. So the answer is, oh, this is square, cos square. Okay, the answer is C. Now, next to the part 4. After a sufficiently long time, the bar moves at constant speed. At this terminal velocity u, the gravity force is balanced by the magnetic force along the inclined plane. And we have found the magnetic field along the inclined plane. And then we have this gravitational force working downward. So if we break the gravitational force, this one is mg sine theta. When the velocity is equal u, terminal velocity, gravity force is balanced by the magnetic force. So it is actually it's just saying that sigma f is 0. That's why the velocity reaches the terminal velocity where there is no acceleration anymore. At this time, f is equal mg sinus theta. Okay, just now we have the f. We already calculated that f is this. Let me copy this one. So yeah, b square d square phi cosine square theta over r equals to mg sinus theta. This is when the phi is equals u. So let's put in the u into the phi. So we have I should make it clear here. When phi equals to u, terminal velocity, no acceleration, which is why sigma f is 0. Now we can rearrange this to get u, mgr sinus theta over b square d square cosine square. So the answer is E. The answer is E. Okay, now move to the last part of number 2, which is part 5. So part 4 and part 5, the condition is just the mass, the conducting bar of mass m already reached the terminal velocity u, so there is no acceleration anymore. So part 5, they want us to find rate of work done by the gravity on the bar. So we know that rate is equals to W over T, which is W is work, work is force, in this case is force, gravitational force times S, because we want work done by the gravity, so the force is the gravitational force over T. Fg here is mg sinus theta, because this is the one that is working along the inclined plane, so not mg but mg sinus theta. S is distance. We know that distance traveled is just velocity u times the time, so we got the distance divided by the time. So we got mg u sine theta, but then we already found out u from part 4, so now let's copy that one. Copy. Here it is. Now let's plug in the variable mg r sinus theta over b square d square cosine square theta sine theta. Now we have m square g square r. Sine square over cosine square, it is just tangent square, divided by b square d square. So the answer is E. Thank you for watching. Good luck for your exam.